Okay, so we talked last time about energy conservation, did some problems with the work energy theorem, did some problems involving energy conservation. And you might think, well, shoot, between energy conservation and Newton's second law, I think I can handle just about anything, okay? But there's a problem. And the problem is that if you go back to this problem here, let's say you have a skier going down a slope, and we wanted to find the speed of the skier at the bottom of the slope. And then we would have to know, for example, the height here, right? And we would have to assume that this was a frictionless surface. Okay. The problem with energy conservation is that energy is a scalar. Okay. And therefore, there's no direction associated with it. So while this is a good method for finding the speed at the bottom, it's not very good for finding the velocity, because the velocity requires you also have the direction information as well. But there's nothing in the energy conservation laws that allow you to extract that. Essentially, you're dealing with scalar quantities, and they're all information about the direction that things are going gets lost in those quantities. So what we would like to do, keep in mind, what was so really cool about energy conservation was that we didn't have to worry about what took place between the top and the bottom. It would allow us to just do a direct comparison between the two. Okay, and we would like to retain that, but we would like to bring in something that has some direction associated with it. And that would allow us to not only tell how fast the object is traveling, but also its direction. And so we need a vector quantity, and we have one called momentum. So we have momentum is a quantity what we call P. I don't know why they use P, but they do. It's a vector quantity, and it's simply equal to the mass times the velocity. Now notice the kinetic energy was 1/2 mv squared. The big difference is, well, of course, there's no 1/2 here, but velocity is not squared here. And this is a vector equation. This is not. So this will allow us to understand the directions things are traveling. However, we need to establish if momentum is conserved. Energy is conserved under certain conditions. And remember what that was. When the non-conservative forces do no work, energy is conserved. So let's take a look at this a little bit here. Let's say that you have a 1 kilogram object traveling at 1 meter per second. The amount of momentum would be here simply 1 kilogram meter per second. And we don't have a special name for this. Unlike like we use joule and watt, they never have come up with one for momentum. So it's just kilogram meters per second. And how much momentum is this? Well, it's a 1 kilogram body, like a textbook, traveling along at about 1 meter per second. Okay, so this is an object, probably more like this, that has a momentum of about 1 kilogram meter per second. Okay, now to specify the momentum truly, I'd have to also specify direction. So it'd be 1 kilogram meters per second, and in this case here, towards your right. So momentum, easy to define, pretty easy to remember. All right, and what's kind of interesting, what's important is if we can establish that momentum is conserved in certain processes, then we can say that the momentum before is equal to the momentum after. And since there's a vector equation, so let's take a look, I'll just draw that down. If we can establish that P initial is equal to P final, then we can establish the direction that things are traveling because this is a vector equation. So under what conditions is momentum conserved? Okay, well, I'll tell you right now, it's not in this one. Let's go ahead and erase this. And to find out what the conditions are for momentum conservation, we go to Newton's second law. Newton's second law says that if we vector sum all the forces acting on a body, we get the mass, I'll say system, of the system, it's the acceleration of the system, okay? Well, what we want to do is we want to see under what conditions is delta P in a system equal to 0. In other words, under what conditions does the momentum of a system not change? Okay, well, first of all, let's just put in here what momentum is equal to. Momentum is equal to mass times velocity. So the question now is, under what conditions is the mass times velocity of an object unchanging? Okay, well, we can go a little bit further here and we can say, well, because the mass of the system doesn't change, it's a fundamental property of this system, then this becomes the mass of the systems times the change in the velocity. Okay, so now what I'm going to do is divide by delta T. Both sides. And I get still 0 on the right-hand side, but look what that is. The change in the velocity divided by the time it takes to change the velocity is our acceleration. So this is just says ma. So this establishes the condition for the momentum to not change. Essentially, momentum of a system is conserved if the vector sum of all forces acting on the body, which is what we call the net force. So in other words, if you look at all of the forces that act on a system and you vector add them and they all cancel, the momentum of that system is going to be conserved. And that means what? The momentum before something happens is equal to the momentum after. Okay, so let's go ahead and examine this a little bit more. So let's see here. Take this out. And you just got to remember, momentum of a system is conserved if the net force acting on the system is 0. Okay. What we're going to have is a body sitting here. And I'm going to hit it with another body. This body is going to be traveling at some speed v. Let's just go ahead and give us these values. 3 and 6 kilograms. And the speed is, let's say, 4 meters per second. And this thing is just going to come in here and smack this 6. And we'll say that they stick together and move out. So after the collision, they're doing this. They're combined to form a 9 kilogram body, moving at some speed that we don't know. So this body is sitting here initially at rest. This comes along, hits it, sticks together, and they move to the right. 1 second. I'll put you on pause for a moment. Okay, so how can momentum conservation help us here? Well, first of all, we have to first establish, is momentum conserved? Okay, so this is the before picture, this is the after. And if momentum is conserved, that means that the momentum of the system initially must equal to the momentum of the system final. Now, the question becomes, what's the system? Well, remember, the system is anything you want it to be. So let's just take a look at the 3 kilogram. If we just make this the system, is its momentum conserved? And the answer is no. And the reason why is it slides across, it hits the 6 kilogram. The 6 kilogram block is going to apply a force to it. And so when the block comes in and it hits it, the 6 kilogram is going to apply a force to it. I'll just draw this here. So here's your 3 kilogram. And the 6 kilogram applies a force to it. Now, the 3 kilogram applies a force to the 6. And the 6, of course, applies a force to the 3. But remember, if we are going to look at momentum conservation, the question is, is the net force on the system equals 0? And in this case here, there is no other force to counteract the force of the 6 acting on the 3. Yes, there's normal force and gravity, those cancel each other out, but there's nothing to cancel, there's a red one. You think, well, wait a minute, what about this one? The block comes in, hits the 6, it applies a force to it, right? Yes, but this is a force acting on the 6 kilogram block, not the 3 kilogram block. If we define the 3 kilogram block as our system, we care about the forces acting on it. And so these forces don't cancel each other because they act on different systems. There is a net force acting on the 3 kilogram block. Its momentum is not conserved. Okay. Let's take out now this. And for the same reason, if we make the system the 6 kilogram block, its momentum is not conserved because there's a force acting on it by the 3 kilogram that's not offset. There is a net force acting on the 6 kilogram block, its momentum therefore will not be conserved. However, if we combine both of them together as the system, then when this block here hits the 6 kilogram, yes, the 3 kilogram applies a force to the 6, and the 6 applies a force to the 3, but these are forces that are now internal to the system because the system encapsulates both bodies. Therefore, these are not forces that act on the system, they are forces that act in the system. The only forces that act on the system is gravity and the normal force, but those cancel because this is on a horizontal plane. Therefore, the momentum of this system is conserved in the collision. Therefore, we can write the momentum before and after. Let's just go ahead and do that. The momentum initially is equal to the momentum of this block. Three kilograms times 4 meters per second in the positive direction going to the right. The momentum after, and we'll just put here to the right. The momentum after is what? The mass times the velocity. And we could guess that it's traveling to the right as well, positive. If I don't know at all for sure, we'll show you some problems where it's not a given. Then I would leave the arrow on top. And then my answer for the velocity will tell me the direction if it's plus or minus. Okay. We'll just go ahead and leave it like that. So now what do we have? Because momentum is conserved, this must equal that. 12 kilogram meters per second must be equal to 9 kilograms times V final. And so we get that V final is 12 divided by 9 meters per second. Notice it's positive here. That means that our direction is to the right. So this is how momentum conservation not only told us the final speed of the object, but it also told us the direction. It has kind of one of the main benefits of momentum conservation is that it gives you direction information. Now notice something, a couple of things. One, Newton's second law technically can be used to solve this problem, but you would have to know the nature of the force between the two, and that may not be knowable. And so to find the acceleration, that might be a job that's impossible to do. Okay. Momentum conservation doesn't care about the nature of the collision itself. The forces in their mathematical description, it just says before equal after. Again, we're going back to symmetry principles. And let's see, there was something else I was going to tell you about this. But I'll come to it here in a moment. Oh, that's the other thing, yeah. Is energy conserved? Couldn't we just solve this by doing 1/2 mv squared equal to, no, the answer is no. You don't know if energy is conserved because when this object hits this one, you don't know if the force that's applying on the 6 is a conservative or non-conservative force. If they are hitting each other with springs, which is a conservative force, then you could also make the statement that energy is also conserved. However, if it's a hard collision, and by the way, if the two objects stick together, it can't be a conservative force. It has to be non-conservative. In this case here, they stick together, energy is not conserved. So you can't set EI equal to E final. But you can set momentum initial equal to momentum after. The conditions for momentum conservation are different than that for energy conservation. Okay, so this is important to listen to. Okay, energy conservation depends on the nature of the forces that act on a system, whether they're conservative or non-conservative, and whether these forces do any work. Momentum conservation is concerned about the net force acting on the system. So totally different conditions, and you have to make sure by the time the exam comes around that you understand those two different conditions. Okay. All right. Now let's take a look at a case where momentum and energy are conserved. And this, I'm going to set it up, and then we'll have to come back to it next time. By the way, you should revel in the fact that this was so easy to do. This was a very easy problem to solve because of the symmetry idea of setting something equal to something else, not having to worry too much about the nature of what takes place during the event. Okay. What I'm going to do now is I'm going to replace the two blocks. Well, I'm still going to use the two blocks, but now I'm going to use springs between them. Okay. And then the next time we get together, I'll use a physics demonstration to show you what this stuff kind of looks like in real life. So now we have the same kind of system. We have our three coming in. But in front of the spring, of the block is a spring. And then we have our 6 kilogram sitting here, and it has a spring as well. Although technically it probably doesn't need one because this one has one, but that's okay. Now, these are perfect springs, ideal springs. So when they do work on a body, they don't they are ideal springs. So they are, when they exert a force on the other body, that force is a conservative force. Therefore, it could do work on the other body and not violate energy conservation. So this thing comes in, we'll still have E equal to initially at 4 meters per second. And this is going to come in and they're going to hit, but they're going to bounce off each other now. Boing. So afterwards, we can kind of guess maybe that this 3 kilogram is traveling in this direction. I won't draw the spring because it's trouble. And this one is moving to the right. This is the final 2, the final 1. This is called an elastic collision. Elastic collision simply means that energy is conserved. Two bodies are nailing each other, but there's no energy loss of the system. And now the question is, how can we solve this with our energy and momentum conservation? Energy is conserved because the work done by this body on this one and this one on this one is conservative. And remember, energy, you only lose energy if a non-conservative force does work. Okay. And we're assuming a frictionless surface here. And momentum is conserved because if you include both bodies in the system, because the only forces acting on the system are the normal forces of gravity and they vector cancel. So we'll set Pi equal to P final, which states that this momentum, which is 3 kilograms times 4 meters per second, this is positive, it points to the right. I forgot to mention this one's going that direction. Plus 0, this one doesn't have any momentum, is equal to, and I'm going to guess that this 3 one here is going to bounce in this direction. And if I make a mistake in that, I'll get the wrong sign. I'll get a negative sign, which tells me that I drew the thing in the wrong direction. Okay, so this would be negative 3, the final 1, plus 6, the final 2. Mass times velocity minus is in this direction, plus in that direction. Again, momentum conservation is a vector equation. You have to put in the proper sign, plus or minus. Well, we could clean this thing up. We could say that this is 12 is equal to, I'll put this one in first, 6 B final 2 minus 3 B final 1. Now notice, 2 equations, 2 unknowns. I mean, 2 unknowns, 1 equation can't solve. But we haven't conserved energy first. And I had told you that these is an elastic collision, means you can conserve energy. The potential energy doesn't change at all because it's all being done on a level plane here. So we can actually just conserve kinetic energy. So in other words, delta E is equal to 0 is from energy conservation, but delta PE is equal to 0 because it's all taking place on a horizontal plane. Therefore, delta KE is equal to 0 as well. So we just simply conserve the kinetic energy before and kinetic energy after. So what's the kinetic energy before? Well, it's 1/2 times the mass times BV squared. Remember, right here. 1/2 mv squared. And your kinetic energies are always going to be positive quantities, no matter which direction the object's traveling. Plus 0. This one doesn't have any kinetic energy. Must be equal to the kinetic energy after, which is going to be what? 1/2 times 3 times v final 1 squared plus 1/2 times 6 times v final 2 squared. So we could go ahead and kind of clean this up a little bit. Let me go ahead and erase stuff. Let's write down our equations. The first one was 12 is equal to 6 v final 2 minus 3 v final 1. And the second one is going to be 16 divided by 2 is 8. This is 24. This is 3/2 v final 1 squared. And this is 3 v final 2 squared. And we end up with 2 equations, 2 unknowns. You could go online because there are simultaneous equation solvers online where you can just dump the numbers in and they'll tell you what the answers are. Okay, so I don't want to go any further. I'll let you work on this to determine. But notice, right now, this is just a math problem. There's no more physics involved. 2 equations, 2 unknowns, and math is a prerequisite for this course. I assume that you're going to be able to solve this. Okay, and by the way, I'm not saying it's easy. This might take a little while because of the squares. But notice something here. The elastic collision is harder to solve. That one that we did before, which is inelastic. So I should define your elastic. E is conserved. So as soon as I tell you that a collision is elastic, you know to conserve energy. And you might be able to conserve momentum, depending on, again, do all the forces cancel? Do all the external forces acting on the system cancel? Inelastic means that energy is not conserved. That's for the IN. And then perfectly inelastic means maximum energy is lost. And you can think of it as sticks together. You can show that when 2 objects smack each other and stick together, that the amount of energy that is lost is the maximum you can lose. That's called perfectly inelastic. But you can think of perfectly inelastic meaning this: the objects stick together. Okay? So I will go ahead and stop it for the time being. Tomorrow we'll pick up again with momentum conservation, finish that off, and then we'll probably start with torques. So until another day, I'll see you later.